Hello, in the previous video we have bitched about the centigrade scale, right? We complained that it's an empirical scale without any theoretical grounding. And we complained that it's a relative scale, it does not report absolute temperature. So a better temperature scale is waiting to be discovered. So the first breakthrough came in about 1808 from the studies of gas laws. Now we can study how the pressure of a gas varies with temperature using any gas, right? We can use oxygen, we can use nitrogen, we can use carbon dioxide, whatever. So with one type of gas, we realize that the pressure varies with temperature according to this graph here. With another gas, we can get another line. With another gas, we get yet another line. Why didn't I complete the graphs here? Well, because experimentally we couldn't reach these very low temperatures, or the gas might have liquefied by then. But then there's no stopping us from extrapolating the lines, right? So when we do that, we realize that all the graphs of all the gases will always intersect at the same point here, at this magical, mysterious temperature of negative 273.15 degrees centigrade. Now, there must be something special about this temperature, right? Cannot be a coincidence. Now, for the pressure of a gas to reach zero, it must mean that the gas particles have stopped their crazy random motion, isn't it? So maybe temperature is a measure of this microscopic random motion, and the coldest possible temperature could be negative 273.15 degrees centigrade. Interesting. Now, the second breakthrough came in about 1848 thanks to this guy called Lord Kelvin, who looks quite scary in this photograph. Now, the Carnot cycle is not in your syllabus, so I'm going to be very brief about this. Basically, the Carnot cycle is about bringing a substance repeatedly through these four thermal processes. And during this cycle, the substance is held at two temperatures, TH and TL. And the cycle also involves some heat input, QH, and some heat output, QL. And it turns out TH over TL is equals to QH over QL. Now, most of us will just marvel at this and stop there, right? But not Lord Kelvin. He immediately saw that this could be the basis for a temperature scale. More specifically, TH could be the steam point, TL could be the ice point. So the theoretical value of QH divided by QL based on the Carnot cycle will give us a constraint to what temperature values we could assign to the steam point and ice point. So with that in mind, Lord Kelvin started to put numbers into his temperature scale. So at the suspected lowest possible temperature, he assigned the number 0. As for the ice point and the steam point, he realized that a pair of numbers that will satisfy the constraints set by the Carnot cycle turns out to be 273.15 and 373.15. This came to be known as the Kelvin scale. And the Kelvin is now the SI unit for temperature. So it turned out to be quite a minor tweak to the centigrade scale. We have very sensibly designed 1 Kelvin to be the same magnitude as 1 degree centigrade. So to go from the centigrade temperature to Kelvin temperature, you just need to add 273.15. But the problem with the Kelvin scale is it's a bit hard for everyone to adapt to this new temperature scale, right? Like, all the numbers are too big. The temperatures we encounter in our daily lives are now too big, isn't it? Imagine you setting the aircon temperature to what? 300 Kelvin? Or you measure your body temperature. What is the fever temperature? Oh man, what is it? 310 or what? So for this reason, we created the Celsius scale. To go from the Kelvin scale to the Celsius scale, you just subtract 273.15. So ice goes back to melting at 0 degrees Celsius and water continues to boil at 100 degrees Celsius. So some students will say, "Che, isn't it back to the same thing?" Well, you must realize that the Celsius scale is built on top of the Kelvin scale for our convenience. And something fundamentally changed when we went from the centigrade scale to the Kelvin scale. The Kelvin scale is not an empirical scale. It's a thermodynamic scale based on some theoretical principle of thermodynamics. The Carnot cycle can be applied to any substance. It's universal and it's not tied to any arbitrarily chosen property of particular substance. It's also an absolute scale. It's not a relative scale. 0 Kelvin is indeed 0 hotness, and 40 Kelvin is indeed twice as hot as 20 Kelvin. Now, before we go, one last thing. Now, at first, we suspected that at 0 Kelvin, at the lowest possible temperature, all the random microscopic molecular motion come to a complete stop. But then later, with new knowledge gained from quantum physics, we realized that it's not possible to have absolutely zero motion. So because of this technicality, we don't say that at 0 Kelvin we have 0 molecular motion. Instead, we say it has minimum molecular motion. Alright, that's all. Ta-ta!